This is Physics Lab 2 Projectile Motion. The purpose of the lab was to model and analyze the motion of an object that is thrown and moves like a projectile using experimental observation and computational modeling. I used a paper ball for object, tracker, glow script, and meter stick for calibration. The model was drawing a paper ball and analyzing its motion, and the fundamental physics principle applied here is Newton's second law, which states that the acceleration of an object depends upon two variables, the net force acting on the object and the mass of the object. So the formula for Newton's second law is F net equals the change in momentum over change in time, which also equals to mass times acceleration. From Newton's second law, we can derive the velocity update formula. And using the update velocity formula, we can also derive the position update formula. And the net force on the system in the experiment is that F net equals to force of gravity plus the force of drag force, where force of gravity is negative mg in the y direction, and the drag force is given by negative b times velocity squared times the unit vector of v. The system in this experiment was the paper ball and gravity, and the surrounding was the air resistance, which is the drag force. The actual motion of the object follows a higher trajectory compared to both computational models. This is the tracker video of the experiment. From the tracker, we can get the initial position and calculate our initial velocity. For initial velocity, I got the first two time intervals and did velocity final minus velocity initial over change in time. For the drag force, I used the x direction because the y direction has gravity applied, and using the x direction, there's no gravity applied. So the initial x was 0.6565 meters per second, and the final velocity in x was 0.4706 meters per second. Using F net equals momentum final minus momentum initial, we get that F net is equal to negative 0.0008 newtons. And by setting the drag force equal to this net force, we get that B is equal to 0.001856. For computational model, first I changed the mass and the position and initial velocity. I also updated the delta t because the video was in 60 frames, and kept b equals 0 for no drag force model. For the net force, I calculated F net using Fg plus F drag and put the formula for Fg and F drag accordingly, and used the velocity update formula and position update formula to keep the velocity and position updated. For Fg and F drag, everything was kept the same except the constant B was changed to 0.001856. This is the model comparison. As you can see, the actual model shows a higher trajectory and took a longer time to reach the ground because there was air resistance and possibly some other factors that affected the motion. And the gravity only shows the fastest time to reach the ground because there's no force acting against its motion. So possible sources of error include human errors when plotting on tracker, which could also give errors on the drag coefficient because they were estimated from the information from tracker. Also, the shape of the paper ball was not perfect, which means air resistance would have caused it was applied unevenly. So what does this mean? Terminal velocity happens when a freely falling object experiences zero net force. In the gravity and drag force model, it shows the velocity slowly reaching a constant value over time, so it does predict the terminal velocity. However, the time was too short to successfully predict the terminal velocity, which means the experiment could be longer or dropped from a higher height. If the object was thrown straight up with the same initial speed, it would take longer to reach the ground because the initial speed in the x direction would also be in the y direction. And when calculated, since the initial velocity in y is larger in the drawing straight up model, the object would reach higher maximum point and also would take longer to reach the ground. Conclusion. In the computational model, the model assumes everything is perfect, which means the object is drawn perfectly and feels a drag force evenly. In the real world, however, the object used was a paper ball, which makes the drag force act unevenly. And also, the paper ball could have spinned in the air, and which causes it to lose some speed. Because of that, the real world observation perceived a slightly different and higher trajectory compared to the computational model.